In this video here, we're going to take a look at loci for conic sections 2. Now, each of the conic sections that we have encountered so far can be defined as a locus of points. So for example then, the parabola is the locus of points equidistant from a fixed point and a fixed straight line. And we can use the properties of conic sections and general points on each curve to find other loci associated with these curves. Now before you continue with this video, just make sure that you're confident with the conic sections from conic sections 1 and conic sections 2. So this includes them, parabolas, rectangular hyperbola, ellipses, and then finally here, hyperbola. Now before we jump into the practice question here for this video today, I also want to include this here. So this little table, right, this is included in your formula book. And this is quite useful as you work through questions like this based on loci. So what this includes here then is the conics that you look at for A-Level Further Maths. So we have an ellipse here. We also have a parabola, a hyperbola, and then finally a rectangular hyperbola. And as we can see here, we have a few different things. So we have the standard form, the parametric form, the eccentricity, the foci, the directrices, and then finally any asymptotes. So this table here can be particularly useful, as I already mentioned, right, as we work through questions here based on loci. So just so you're aware then, you might also find this useful here as we work through these questions. Okay. So that concludes our introduction here to loci for conic sections 2. Let's just work through a practice question now for loci. So let's just have a go then at this one practice question here for loci for conic sections 2. So as we can see then for this question here, we have the ellipse E, which has this equation here. So this is just the equation of a standard ellipse. We're then told that the line L is a tangent to E at this point here, P. And for the first part of the question then, part A, we want to use calculus to show that an equation for L is given as follows. So for the first part of this question here, nothing too challenging, and it's not really associated too much with loci. That's more of the follow-on question here for part B, but it does set us up to answer part B. Okay? So for part A then, where do we begin here? Well, with this point P here, so P has coordinates of A cos t, so A cos t, and B sin t. That should be a B there, apologies. B sin t here. B sin t. We'll fix that on the worksheet. So B sin t there. Well, what this tells us here then is my parametric equations are x equals A cos t. So A cos t and y is equal to B sin t. Okay. Now, we want the equation of the tangent here, okay, at the point P. So if we want the equation of the tangent, what that means then is we need the gradient at this point P. If we want the gradient at that point P there, we also need the derivative, dy by dx here, okay? So dy by dx here. So dy by dx here is equal to, so based on parametric differentiation, this will be dy by dt. So dy by dt here, all over dx by dt. Okay. So if x equal to A cos t, then let's do it over here. Dx by dt. Dx by dt here would simply be minus A sin t. And dy by dt here, nice and straightforward. This would be B cos t. Okay, so dy by dt here, that's B cos t. We get B cos t there, all over dx by dt, which is minus A sin t. Like so there. Okay, so now for the equation of the tangent here, all we're going to do is use y minus y1 is equal to m times x minus x1. Okay, so therefore for the equation of the tangent here, so for the equation of the tangent, this will be given as, so like I said then, all I'm going to do here is use y minus y1 is equal to m times x minus x1. So x1 is A cos t, y1 is B sin t. So I get y minus B sin t is equal to m. So this is my m here, B cos t over minus A sin t. So b cos t all over minus a sine t, like so. And then we times this by x minus x1 here. That's going to be x minus a cos t, like so. Okay. So let's times through then by minus a sine t here. So what do we get then? I get minus ay sine t. I'm going to get plus ab. So minus b sine t times minus a sine t. So that's plus ab. So just be careful with the signs there. So plus ab sine squared t. Sine squared t. We then have b cos t times x. That's bx cos t. So bx cos t there. And then b cos t times minus a cos t. That gives us minus ab. So minus ab cos squared t. Okay. So let's just keep going here then. So this is what we need to obtain, right? So ay sine t plus bx cos t is equal to ab. Well, we're getting there. So what I'm going to do here then is add ay sine t to both sides. That would give me the ay sine t and the bx cos t here on the right-hand side. I'm also going to add ab cos squared t to both sides here. So I get ab sine squared t. So ab sine squared t here plus ab cos squared t is equal to ay sine t plus bx cos t. Okay. Well, at this point here then, I can factor out the ab. So I've got ab bracket sine squared t plus cos squared t. And you should be aware then that sine squared t plus cos squared t is equal to 1. So I get ab times 1, which is just ab. And that is equal to ay sine t plus bx cos t, exactly as we require. Okay, so as required there, and proof complete. Okay, so there we have it. That gives us the solution to part A. Now for part B then, I'm not quite sure whether I'm going to have enough room here to answer part B alongside part A here. So let me just quickly clear the screen here and then we can have a go at part B. So we've cleared the screen. Now let's have a go then at answering part B here. Now for this question, even if you couldn't answer part A, so even if you couldn't derive this result here, you can still use this result to answer part B. Okay, so you didn't actually need any of the working in part A to go on to answer part B. We just need this result here, which is already given, right? So for part B then, it says, the line L cuts the x-axis at A and the y-axis at B. We want to show that the locus of the midpoint of AB is given by this result here. So where do we begin here? Well, the first thing that I do here then is just quickly draw a diagram. It doesn't have to be perfect, but just so we can visualize the problem at hand. I've got my y-axis here. That's my y-axis. We also have our x-axis here, like so. And let me just quickly attempt to sketch the ellipse E here. It won't be perfect, but you get the idea. Okay, let's say that that is my ellipse. So it looks maybe a little bit more like a circle. I'm not too sure, but you get the idea. This is just my ellipse E here. Okay, so I've got this point P here. That's the point P. And we have the tangent to E at the point P. So something, say, like this. Okay, that's my tangent there, L. Now this cuts the x-axis at this point here, A. And it cuts the y-axis at this point here, B. Okay, and what we want here then is the midpoint of AB. So what that means then is we need the coordinates of A, we need the coordinates of B, and then we can go on to find the midpoint of AB. Okay, so for A here, this occurs when y equals 0. Okay, when y equals 0. So all I need to do here then is substitute y equals 0 into the equation of the tangent. Okay, so ay sine t, that's just 0. And then get bx cos t. So bx cos t is equal to ab. All I'm going to do then is divide through by b cos t. So therefore x equal to ab over b cos t. So ab over b cos t. The b's will just cancel here like so. So that's a over cos t, which we could also just write then as a sec t here. Okay, so that's for a. Let's just underline that there. Doing the same now for b here. So for b then, this time now this is when x equals 0. Okay, so when x equals 0 here, again, just substitute x equals 0 into the equation then of the tangent. So this part here would just be 0. I get ay sine t is equal to ab. So ay sine t is equal to ab, like so. Again, just divide through now. So divide through by a sine t here. So y is equal to ab over a sine t. A sine t there. The a's will just cancel here. I just get left with b over sine t. So b over sine t here, which is just the same then as b cosec t. Okay. So the b then, this has coordinates of 0, b cosec t. Okay, like so. And then for a here, this has coordinates of a sec t, and 0. Okay. So at this point then, for the midpoint here, so for the midpoint here, all we do here is we average these coordinates, right? So nice and straightforward here. I get 0 plus a sec t over 2. A sec t all over 2. And then for the y coordinate here, 0 plus b cosec t over 2. B cosec t over 2. And this just gives us then a half a sec t, or a sec t over 2, whichever you prefer. So a sec t over 2. And then for the y coordinate here, we get b cosec t over 2. Like so. Okay. Now we're getting pretty close to obtaining this result here. So for the next step here, this is probably the trickiest thing to kind of spot here, but what I need to do now is use a trig identity. Okay. So at this point here, just gonna make a note then, we're going to use sine squared x plus cos squared x is identical to 1. Okay. We're going to use this result here. Now, at this point here, I've got a sec t over 2, b cosec t over 2. So I need to think about these now in terms of sine and cos rather than their reciprocal trig functions. Okay. So this here then is just the same as a over 2 cos t. I'm running out of room here, maybe. We'll give it a go. Then it's going to be b all over 2 sine t. Okay, like so. So I can rearrange this here then to make cos t the subject. And I can do the same here with the y coordinate. So if I do that over here, what I've got at this point is x equals a over 2 cos t. I've also got y equals b over 2 sine t. Okay. Making cos t the subject here, what would that give me then? So cos t, divide through by x as well. So I get cos tx is equal to a over 2, divide through by the x then. So cos t is equal to a over 2x there. Like so. I'm doing the same here then for sine t. Sine t is equal to, so that would be b over 2y. Okay. And we're pretty much there now. So replacing sine x here with, well, it would be sine t here with b over 2y. I'm doing the same then with cos t, so that's going to be a over 2x. What we get here then is b over 2y all squared plus, and then get a over 2x all squared is equal to 1. So now if we evaluate this here then, I get b squared over 4y squared. I get b squared over 4y squared. As you can see, this question is quite lengthy. We're pretty much running out of room here, but we're nearly there. I then got a squared over 4x squared, like so, is equal to 1. And this is the result that we wanted to obtain. They wrote it as a squared over 4x squared first, but it doesn't really matter. But I'll do it anyway. I'll do it in a different color here. Let's do it in red. We obtain a squared over 4x squared there, plus b squared over 4y squared there. And this is all equal to 1 there. There we have it. So as required, we've obtained the desired result. So some beautiful maths there, pretty much to get us to that point. But hopefully that does make sense now as we've worked through this step by step here. As you can see, these questions can be quite long. And there is a few little points in the question where you can make easy mistakes, but hopefully overall, not too challenging. Okay. So there we have it, right? As I mentioned, we're just looking at the one question for this video. But that gives us the solution then to this one practice question here for loci for conic sections 2. And that actually brings the end then of this video here on loci for conic sections 2.